CAD drawings anymore. Okay, you can bring it in Revit. Since it's a 3D, so you can actually see the sizes also. Have anybody used Revit? Little bit. Okay, so you can actually import that in Revit, and that's it. You actually see the sizes. So yes, when you print out in Revit, you can do the plans, but physically you can actually see the 3D. Okay, so that's how. So what we are going to do here is first we will develop the model, and then we will analyze it, and then we will run it. Okay, so develop the model is that's the model we are going to do. So it's probably the easiest, but by the way, you are not allowed to use a box. Your architectural drawing cannot be a box. Okay? This is a box, so you cannot have a box. You can have all the geometries, all the carved geometries you want, okay, but you cannot have a box. You can make a shape is easy. Okay. Use your imagination. Okay. Life okay. Those are easy shapes. Okay. Give some imagination. Okay. You like Frank Gehry's.
But can I ask you a question? Because like I was watching this stuff. So like, as engineers, are we in charge of doing like skin engineering? I can't explain it, but like let's say you have like design elements that are like hanging off the building. How do we model that stuff?
Yes. Say for example, I'll give you a quick example. If you have been to Beverly Hills, there is a car museum, right?
Okay.
Have you seen a car museum? There is a museum of cars, right? And if you see the front part is actually a decoration. Okay, it's a what is that called? It's not a fascia. It's kind of like a structure just for decoration. It's not structural taking load. It's just showing that. You have to design that. Okay.
Yeah, so can we use software like RAM to do that, or?
RAM can do that, but RAM usually don't do that. The exterior claddings, what we call claddings, RAM doesn't do that. Okay, but RAM can. There are elements of RAM which can do that. Okay, not all of it. Okay, now those are like more like, I should not say that those are important, but not like what I like. I like more main structure. Those are for engineers who can do actually non-structural design. I know one of our ex-students, he was a very good student. Their company does that, all the exterior, all the screens in front of a building. Those are not part of the structure, but those are kind of like hanging from the structure. So you have to design them. Okay, so we are going to model it first. Before we model, we want to see the criteria. Okay, member loads. We are using the IBC code. IBC and CBC are the same, and there is no change anymore. So these are okay. The only thing that is the thing is self weight. I mentioned in the previous class, so it's a repetition for you who took the concrete class. Is that I don't want to. Basically, it says that RAM will generate or calculate all the loads by the beams and the columns and the walls. So RAM can calculate the load. Okay. The problem is only on the slab. If I say I needed this slab, RAM can calculate the slab weight also. But usually one slab on top of the slab, we will have like a floor finish of the slab. Okay. So if you want marble, that's an additional 40 psi sometimes. If you have a roof tiles, then you have something else. Okay. So in those cases, I don't like RAM to calculate the weight. I like to give it as a weight. Remember in our classes or exams, I gave like 70 psi dead load. That 70 psi is the self weight. Okay, so I'm going to give it as a self weight rather than allow RAM to calculate it. So that gives me some flexibility. So I'm going to uncheck that. This one. Are you getting the board or are you getting my face?
A little bit of both. It's a nice silhouette.
Do I look okay?
Great.
You should have told me, and then I could have like a clean shaved and
No, it's
some
all
gels.
all I see is silhouette.
Yeah.
That's it.
Huh?
Okay.
Yeah, you know.
I mean, you're putting in YouTube, and people will look into that. Come on. Okay. So I'm going to click on that. Okay. The other things is RAM. Interestingly, RAM master seal. If you see RAM AIAC, that means RAM will take the AIAC code and this book and get all the values from this book. By the way, I did not mention this book. Actually, it has a CD. I don't know whether they send it a CD or flash drive. You can buy a CD or a flash drive, which means you actually get all the tables that are listed in this book in an Excel file. Okay. So what we do as a structural engineer, we take those files and actually take those numbers and convert it with our own spreadsheet. That means we generate our own programs. Okay. That's the common practice in industry. Okay. You don't have to write everything. They have everything in Excel file. I had that previous ones, the 13th and 14th, not the 15th edition. I think they charge for it. It used to come free, now they are charging it. Okay, so RAM uses those Excel files. Okay, so click on that. That's the RAM modeling part. So we are going to use the RAM modeler. So right now there is nothing here, no platform. Only thing that is given is RAM steel. That's the default. Originally, RAM was developed for steel structures, and in 2009 or 2010 they started adding concrete structures also. So it was primarily for a steel structure building. And RAM, that's why RAM is good in steel structure. Right now there is no platform, so the way we model it is we will take a floor plan. Okay, the architects usually give us the floor plan, like first floor, second floor, ground floor, or like that. Okay, we take one of the floors and design that, or actually model that, and then we go to the next floor. Sometimes when we go to the next floor, we copy the first floor, the one that we developed, and then make modification on top of that, because that's much easier. Sometimes we redraw everything. Okay, so also in an office building, typical office buildings, your first floor is different than the second floor, but second, third, fourth, it's almost like identical. Framing wise, loading wise, okay, should be more or less identical. Okay, so what we are going to do here is we are going to draw, or we are going to model a typical floor first. Then we will copy that typical floor for first floor, and if we have time, we will change it. If we don't have time, we will not change. First floor has different loadings. Usually they have a lot of storage. The corridor live loads are different. That's why we will change it. And also at the roof level, we can change it because roof live loads are also changed. Okay? So let's do a typical floor first, and then we'll see. And the main thing that we are going to do is these three: prop table, layout, and story. Prop table means we have to give the properties of the loads, properties of the decking. Layout means we are actually laying out the model, and story means we will give the story information. In layout, there is type, grids, columns, beams, and so on. We will follow each of them, according to their position. That means we cannot just jump from type to grids. We have to follow type, then grids, then columns, then beams, and so on. Okay, that's how we are going to do. So let's go for type. Select. There's nothing given, and I'm going to say I'm going to use a typical floor first, and that's why I'm going to add. Right now there is nothing here. I'm going to select that. Also, since I'm here, I'm going to say that okay, I will have another first floor and add, and I will have a roof. Add. So I'm going to first develop the typical floor. Select. Right now there is nothing here, so I'm going to do that. Layout tab is done. Then if you look into the tab, selection is done. Copy. That's where I'm saying that I will copy the other floors from typical floor. So that's one thing. Another one is import from DXF file. That's where we usually, when the architect sends us a CAD file, and we take the CAD file and convert it into a DXF file, and then import that DXF file in RAM. That means we already get all the information that the architect wants us to know, like the location of our columns, location of all the grids, okay, location of our walls. Okay? So if the architect wants us to use there, we can use it. Okay? So that's an very, most of us do that. Right now, we will go to the next item, which is grids, and I will create a grid, and I'm going to give a name. Orthogonal. Orthogonal means like perpendicular. And I'm going to add, and then select, and then edit grids, which is basically what we are going to do, like 1, 2, 3, A, B, C, D. So first grid in the X grid means the ones that are vertical, okay? And the first grid is 1, grid coordinate is geometry, coordinate is 0, and I'm going to add them. Now if you look into that, I have like 2, 3, 4, 5, they're all equally spaced, right? So if they're equally spaced, I can generate one, and then I can place it. So I can use the grid spacing as 30 feet, and number of additional grids, probably I will add another 4 of them, and I'm going to say add. That means you can see they automatically generated the other grids. Same thing I'm going to do for Y grid, and the first one is A, and the coordinate is 0, 0, and spacing is 25 feet, and I'm going to say additional 4 grids. So A, B, C, D, E. Yes.
Can you add 2 different types of geometries on the same grid? Like you do this and you add a radial and
yeah. Okay. So we are done with the geometries. So I'm going to say add. You can always add another.
and you'll go to the same plane with the same origin.
Yeah.
Okay.
Yeah. Same medium. It's just a grid. Plane you are defining as typical. That's your plane.
Yes.
So we are done with the grids. So we'll just click on that. Okay. And since there is nothing, I need to see the grids. So click on this. Select grid system. And for a typical floor, I'm going to select the orthogonal, and now it shows all the grids.
Wow.
Wow. You are impressed with this one only?
No.
You'll be impressed. Okay. So we have the grids. Okay. Now, what is next? Type is gone, grid is gone. Then we have to create columns. Okay. Usually, if you look into that, the columns are added on the intersection of the grids. Okay. So I need to kind of like add on grids. Click on that. Now, if I add on grids, there will be columns like that. Usually, I'm going to use a white plain section. I do not know the size yet, but we will learn it. Okay, or we will design it. At the beginning, I will say that let's start with gravity framing. Okay. At the level of moment frames and grace frames, those will be lateral. Okay. But we can always change the property. Geometry is I section. You can use cube, rectangular HSS or round HSS if you want. But I like this one because that's more commercial one. So single, if you click on that single, it will click on the single intersections. But if you know that you will have columns everywhere, you can do right click and do a fence, click and fence it. You will be impressed the whole day today. Which is good.
For in reality, they change from like side to side, right?
Orientation?
Orientation, yeah.
Yeah, we will do that. No, I'm happy that at least I get somebody who's excited. Okay. Excited means fine, but you have to show how you are doing it. Okay, that's the excitement I get. Okay, so we are showing the columns, but not done properly. Okay, we will have to change some of them. Now, after the column, we will get the beams, and if you see the major ones, the girder ones are connected between columns and columns. Okay, so we connect them first. So add on grids, and again I will say that my first beams are gravity beams, composite. Okay, that's a default. Composite is basically, you will learn it, not probably, the last topic of our course, which is the composite beam section. And actually that is not part of our syllabus. I'm just adding that because you need to know, because it's been done, or it's always been there. Composite sections are like when you have a deck on the top of the beam, and the deck carries concrete, and if there is a bending, positive bending on the beam, that means top part is in compression and bottom part is in tension. And if it is top part is in compression and the top part of the beam has a deck which carries concrete, and the advantage for concrete is that it can take a lot of compression. Okay, so if we are providing concrete on top of the steel beam and it is in compression, why don't we take the advantage of concrete being there, take the compression? You follow me? And if that is the case, then a lot of the steel does not need to take the compression anymore. That means the steel beam is solely for taking tension. Okay, so normally half of the beam takes compression and half of the beam takes tension. If the whole beam takes tension and the concrete takes compression, then I need reduced size beams to take the moment. Okay, you follow me? So that's why we want to use composite action. The only thing is, the beam has to be in positive bending. That means it has to be the positive. That means compression should be in the top. If it has a negative bending, tension in the top, concrete cannot take any tension, so it will not work. Okay. So composite action only works for positive bending. Where is the positive bending? When there is a gravity load and the beams are simply supported. That's when you have positive bending. Okay. If you have a negative bending, say for example moment frame or brace frame, you'll have a negative bending because it goes laterally. So your bending moment diagram, half is in positive, half is in negative. That's not going to work.
Unless you like you're putting concrete, right?
What do you mean by that?
So let's say you pour the concrete and then you separate at the point of where the moment changes, then you have two positive moments for the concrete.
I don't understand what it is.
So the reason you have a negative moment is because there's another support in the middle, right?
No.
Then how can you get a negative moment if it's still supported on both sides?
If you have a fixed connection, if you have a fixed connection, it is a negative moment. Okay. So I'm going to add beams like that. Now again it is time consuming. If I know, I can go a fence and I can do that. Right click. Oh, you didn't say wow.
Wow.
Okay. Now you'll say wow. Okay. Now I have to, if you see, I have to give intermediate beams at 10 feet intervals. So I can say go layout, beams, add off grid, and I say parallel to beam and 10 feet. Okay. And click. Like that. Again, it's time consuming. So if you go layout, beams, add generation, and I'm going to say number of equal spaces per beam 3, add, and if I say will automatically generate.
So equal spaces, 3
Spaces. Okay.
So you do not have to calculate.
10, 10, 10, or 9, 9, 9, or whatever it comes up. Same thing here. Okay.
So my beams are
Done. Actually. The next step is I know that I have moment frames and brace frames, right? So I have moment frames these three, this one, and I have moment frames here, and I have brace frames these two, right? Okay. So let's give them. Now, since moment frames or brace frames, what are those? Moment frames is basically beams and columns. Only thing difference is their connection, and they're supposed to take lateral loads instead of gravity loads. So all of these in the middle are all, I'm saying that these are gravity loads, and the connection between this beam and this beam, and that beam is all simple connection, okay, bolted connection. That makes my life easy. That means these beams will be all positive bending moment, and they will be composite beams. So let's change these frames to frames, okay? That means I need to convert that column to take lateral loads, that beam to take lateral loads. How I do that? I can use layouts, columns, and then change properties. Okay? Now if you see columns, this one, and if you click on this one, they are basically same thing. Okay? These are all listed here. Okay? So either you can go layout, columns, or you can click on that and you can change. So I'm going to use this one, change column, and change the framing first. Okay? Framing from gravity to lateral. Okay? Are you with me?
Yes.
Okay. Another thing is, if I'm saying that framing is in this direction, look at the column orientation. It is connected with the weak axis, right? I want to get the maximum possible stiffness in that direction. So I'm going to change the direction, which is orientation, and I'm going to make it like that. You follow me? That answers your question. Okay? And I'm going to use a fence to convert them. You see, now it's red means it's lateral and the orientation is same. Same thing I'm going to do here. What about these ones? These are lateral, but the orientation should be same, right? So I'm going to right click and just change, the framing is already lateral. I'm going to change it to this orientation and say that like that. Okay. Now the columns are done. I need the beams to be done. So I'm going to go layout, beams, change properties, and the framing should be lateral, and composite flat. Do I need composite flat? No, we expect that it will have negative moment, so don't worry about composite flat. Okay, it will be non-composite. Even though if it is shown as composite, it will be non-composite. You don't have to worry. Another thing is, what about the orientation for the beams? Beams are always oriented in one way. Beams are not flat. Beams are always vertical. So beams are always rotation about their strong axis. So right now all of them are showing as moment frames. For the brace frames, we have to do it in an elevation view once we have the story option. Okay, so we'll pause it for a while for the, leave it for a while for the brace frames. Are you following me? All of you? Okay. So we'll come back to the brace frames when, or defining braces when we are in a position to give, we have the story of, story defined. Okay.
Now, what is next?
Slab. Right now these are all showing as the center line of the beam, so my slab cannot stop here. Okay, my slab has to go over the half center line and then go at the end of, at least at the end of the beam, at least at the end of the column. Okay, so we need to kind of like have an overhang from the center line of the beam. Usually I give 12 inch if there is no shade or anything, no extra. If the architect wants 2 feet, he can give it to us and we can actually model it. So I'm going to give a slab edge and I'm going to say it's a 12-inch overhang. Now, overhang in this direction or outside? It must be outside, not inside. Okay? So I'm going to use an overhang, and left and right means if you try to give one by one, then you follow your path and find out whether it needs left or right to give your overhang. Right now I'm going to say that whole perimeter, so it's drawn a slab edge on the whole perimeter.
Okay? Are you with me?
Now, next thing is I need to give slab deck assignment. I need to assign some decks. Okay. Right now there is no decks are assigned, so I need to assign the decks. So to do that, I need to go to the prop table. Prop table and decking means I need to use a deck. Now the decking that I use commercially is Varco W3. I'm just giving a name. Concrete thickness above fluid is 3.5 inch. Stud length 5.5 inch. Unit weight, right now it's lightweight concrete. I want to use regular weight. F Francis is 4 kg. Effective thickness is 3.25.
Poisson's ratio is 0.3.
So these numbers, take a picture of that. You will be using that. Okay. Now, do you follow what I'm doing here? What is the deck size? Okay. So if I'm going back, what is covered to?
I'm going to show you what
Is the actual deck I'm using.
Okay. I'm using this one.
Varco W3 normal weight concrete 6.5 inch. The deck looks like that. If you look into that, this is the deck. It's a kind of like a white flange W shape or W3. And what W3 means, this length from the top of this one to the bottom is 3 inch. Okay, and it looks like almost like a W. So if you look into that, there is a groove here and comes back like that. Weight of the concrete is 60 psf. Remember in our exams we gave like 75 psf or 80 psf. That's where I got that load. Okay. And which means I have another 3.5 inch content on top of that fluid. Okay. So total is 3 inch plus 3.5 inch is 6.5 inch. That's the depth of the concrete. On top of the fluid is 3.5 inch. Are you with me? Okay.
So,
If you see, I'm saying that concrete thickness above fluid is about 3.5 inch. Stud length. Stud length means what are those studs? starts are okay. Starts are basically these ones. Okay, what is that? It's kind of like a bolt welded to the bottom of the start, and the deck as well as the top of the flange are all welded together. Okay, so it's a one single. And if you look into that, where are my starts? So why we need them? We need them because the concrete can start moving on top of the steel deck. So we need to prevent the concrete to move out or concrete movement. That's why we provide start. This acts as a shear key. It prevents the movement of the concrete as in shear. I want to show you.
Physical starts.
Okay. So if you look into that, that's how the starts are laid out. Okay. Now they are not laid out that spacing wise they are much more closely, about 12 inch on centers. There are some pictures of the start. Anyway, fine.
Okay. So that's another 5.5
inch. Okay. I have total 6.5 inch. Out of that, start has to come on. Now, start has to come on above the fluid. Okay. So that's 3 inch.
The rest is same.
Effective width thickness is 3.25, not 3.5. 0.3, and 3605 is the concrete's modulus of elasticity. If you are using 57,000 root F prime C, it will come out like that. Okay. And I'm going to say add. And I'm going to say okay. Now my property of the deck is defined. I will go back and slab, and I'll say deck assignment, and I'm going to say that this is the deck, whole diaphragm, find out. Okay? So I already defined the deck assignment. Now, say for example, I want an elevator core. Okay? I want an elevator core in this zone. Okay? So what I need to do, I need to kind of like open the slab. I did not show it in concrete, but listen. So go to slab opening, and I'm going to say that overhang 12 on the left, and if I'm saying that I have an opening, the opening should be inside, overhang, not outside. Okay. Already opened up. The program knows where to open up. Now remember, I opened up any opening that you may have in a slab system, doesn't matter whether it's a timber or plywood shear wall, plywood roof or floor, or if it is a steel, or if it is a concrete. It has to be bounded by beams. That means we need to stitch it.
Otherwise, there will be
the possibility of crack generation and crack propagation. So always you have to provide a boundary for an opening. Okay, I'm just going to be leaving with that. Now what is next? Loads. That means I have to find out loading. Okay. So the loading is not there, so I have to go back property table and define some load. First thing that I will do is the surface loading, PSF loading. And I'm going to say that dead load is what? 75 PSF. Okay. Remember, I showed you 60 PSF for the deck load, plus another 15, right? Additional floor finish and so on. So 15 PSF. Construction dead load. What is construction dead load? Construction dead load is the load when we pour the concrete on top of the deck. Okay. So what is the problem? When we pour the concrete on top of the deck, concrete is what? Wet concrete, right? It does not have any strength. It only, what it does is it gives the weight to the deck, and deck it takes the load and put it on the beam. That means those beams have to be designed as a regular non-composite beam. You follow me what I'm saying? Okay. Earlier we defined that, okay, all the beams should be designed as a composite beam. Yes, but when? After the concrete is hardened. Okay? But before the concrete is hardened, the beam has to take the weight of the concrete. Okay? The beam has to be designed based on. So what is the difference? Well, the difference is the beams are only taking the dead load of the concrete. It is not taking any live load or the floor load. It's just taking the weight of the concrete. That's why I am giving a 60.4 PSF as the dead load of the concrete. Okay? There is no additional floor finish. There is no live load added. Now, that's why if you have seen that, and I showed you, usually when we design steel structure, we don't design steel decks to take loads with shoring. Okay? Because the shoring of the decks are costly. The decks are steep enough. It's a steel deck, so they are steep enough to take the loads by itself. And that is why we don't span them more than 10 feet. Because if it is more than 10 feet or 20 feet, 30 feet, the deck will collapse without shoring. Okay. So we are reducing the shoring cost, but at the same time we are adding beams in the wall. Okay. So I'm going to use that live load 50 PSF or 40 PSF. 40 PSF live load, reducible, yes. If it is at the roof level, you can click on that. If it is like more than 100 PSF, so it's a storage, don't use that. Okay, use storage, that means it cannot be reduced. If it is, you do not know, but it's more than 100 PSF, it's unreducible. Okay. So we are going to say add, and we are done. Huh?
About construction live load.
Oh, I didn't give it?
No.
Oh, okay, sorry.
Why did I miss that?
Sorry, I did. Alright, oh, this one. I need to change, so, partition, I should have 10 PSF, but I forgot that. Construction live load. During the construction, people will walk on top of that, so your beam has to take that. And usually that's about 25 pounds per square feet. Mass dead load. Mass dead load is for seismic force, because the seismic force acts at the center of mass with the mass, right? So I need mass dead load is the 75 PSF at least. Sometimes we add half of the partition load, another 5 PSF, maybe 80 PSF. If you think that your mass could be a little bit more, feel free to add that. Okay? Now don't add like another 200 PSF. It's like maybe another 10, 15 would be fine. Not more than that. And then I need to change it.
Yes.
Question? Now we also want to give a line load. Line load means it's the wall load. Now usually a building will have a perimeter wall, that's fixed. Internally they have partition walls, that's not fixed. So I'm going to use a perimeter wall. Dead load is 0.18. I'm saying that wall on 1 square feet of the surface area of the wall is about 15 pounds per square feet. 12 feet high wall, so it's about 180 pounds, means 0.18 feet per feet. Okay? So I am going to use that. Walls doesn't have construction dead load, walls don't have live load, walls don't have partition load, not that. If you want, you can add wall load as your mass dead load. So you can say 0.18 feet per feet, and you are going to add that.
Right?
There is no live load. Okay.
Now, why we need that wall?
Also, if it is a glass wall, remember that on glass walls cannot deflect a lot. That means the beams below the glass needs to be designed for very small deflection. The amount of deflection allowed is 0.5 inch. Okay, so that's why you need to know where is your wall and how much load it is going to give it to the beam. So the beam cannot deflect more than 0.5 inch. Okay, I'm going to say okay. Now let's apply the loads, surface load, and I'm going to say this is the floor load applied everywhere in the diaphragm. Live load, this perimeter wall load is applied at the whole perimeter. So that's my perimeter wall load. Okay, I am more or less done with the design or with the modeling of the typical floor. And as I said, I will convert or copy them for the first floor as well as on the roof. So how do I go? Go here, first floor doesn't have anything. So go layout, type, copy, and copy everything from the typical floor. Done? Okay. Also go to the roof level and layout, type, copy everything from the typical floor. Okay, done. Okay. Now roof live load, you may want to change it. If you want, you can change it. Let's see. Let's say roof live load, and we are going to use roof. Usually have less amount, but we are going to say that 20 psi. The dead load remains same. Roof doesn't have. Roof should not have any partition load. It's a roof, and I'm going to add that. I'm going to say okay. Layout, loads, line load. Okay. Layout, loads, surface load, and I'm going to say okay on top of that. Now that's the roof live load now. And also I am on the first floor. I don't need to change the loading, but only thing that I need to add is the foundations, which is our next step. Foundations will have individual column foundations and also moment frames and brace frames. I need moment frames and brace frames to be continuous foundations. So layout, foundations, individual column footing, add, and I think I will not change anything. Fans. Okay. These are my columns which needs individual column foundation, and I will need individual continuous foundation. Okay. So foundations are done. What else I need? Frame numbers. I'll do that. Now my typical floor, first floor and roofs are done. So I need to give story information. So story information means first floor, and splicing means do you want to change the column sections at that level? No, I want to change the column section at third floor level. And floor to height is that. What did I do?
Change the number.
First floor, no, add it. Then second becomes typical, add. Third becomes typical, but I want the splicing. Fourth, typical, no splicing, add. Fifth, no, typical, no splicing, add. And sixth, I'm going to say it's the roof. That's the end of the story. That's the end of the column. Then okay. Now I want to see whether it's working. Yeah.
Wow.
This is my building, the frame of the building. Okay. Okay. Now remember I mentioned that I will give brace frames on the elevation. Now I have an elevation. Before that I did not have any elevation because that was only one story. So I'm going to go click on that and click on that. And I'm going to give some braces and layout braces at standard. I will use chevron. Okay. FY should be 46 KSI because I'm going to use HSS rectangle. And I'm going to use a fence to give me the braces. Okay. Also, for this program, you need to give the brace sizes also. Okay. The other parts you don't need to give any size, but for the braces you need to give sizes. And I'm going to use rectangular HSS. Say for example, I'm going to use 12W HSS 12 by 8 by 5 8. That size. And if I click on that, that will show me all the sizes here. Okay. Same thing, I need to do braces here, and I'm going to use the chevron. And I need to give the brace sizes. Okay, I'm done.
Now
The other side.
braces.
You're on one side and you want to touch the other side. You just click on the.
I'll show. So, if we done so.
Go to the elevation
Yeah, I
and
understand.
click on that, you will get that. Okay, so far our model is done. I want to check whether my integrity is fine, so I will check with the integrated, which is means gravity and framing. 120 warnings. Don't worry about warnings. Okay? As long as it's not an error. Okay? Don't worry about the warnings now. You will see that all the frame column sizes are not given. Okay, so it expects you to give the frame sizes like moment frame or brace frame sizes. I'm not going to do that because I want to do that later. Okay? If I do that now, it will change. It will be changed. Okay?
So I'm not worried
As long as there is no error. Okay, error will be always with a red mark. So don't worry now. By the time that's okay, I'm fine. And we are done with the modeling part, so I'm going to now into design phase, and that's the beauty part of it. Okay, the beauty part of design is that I'm going to click on the beam designs first, then the column designs. Right? Beam designs. Say I'm going to use a typical. Before we design, we say what is the design code, and I'm going to use the LRFT. Now, unfortunately, my version for this RAM is 2015, so I don't have the 15th code. You will have it 360-15, and I prefer LRFT, so I'm using LRFT code. Okay, it will not be changed that much, but you have, if you download it today or now, you'll have that this should be AISC 360-15. Okay. Now, do you know where is that actually the code in that book? The book gives you all the tables of the geometry, right? That's not the code. The code is actually the chapter 16, the spec. That's your code. Okay. When we say AISC 360-10 or 360-15, that's the chapter 16 we're talking about. So I'm going to use those are as my normal. Deflection criteria, I'm going to use that. Okay, don't worry about that. Camber. Do you know what is a camber? Camber means when it is a steel beam, right? So it's even for self-weight, it's going to deflect. It's very elastic, right? So what we do is, if we expect the beam to deflect when the loads are applied, and we will calculate how much deflection it will be, and 80% of that we will say that okay, that's instead of making flat, okay, if it is a flat, then due to the load it will be like that. Okay, so what we do is tell the fabricator, don't make it flat, make it something like that. So when the load is applied, it becomes straight with the load. Okay, that being, this is called cambering, and that is how much we will specify how much we want. 1 inch to 1/4 inch, or depending on how much it will be deflection weight. Okay, so here what we are going to say is that 80% of the dead load should be used as camber, and the camber should be 0.25 inch, and the maximum camber is 4 inch. Actually, I don't want 4 inch, because 4 inch cambering, you will see that. If the beam deflects 4 inch, you will see that okay, it's 4 inch down. Don't allow it. Okay, for a 30 feet span, we will say 1.5 inch is fine.
So I'm going to use
a 2 inch, and also I'm going to do the same thing for non-composite beams. Okay. Now I'm going to design it. You're not saying wow. Already designed.
That's a lot.
Why are we taking an exam?
So your beam sizes, if you see W12 by 19, 10 means not 10 stops in the middle, and C equals 1, that means cambering 1 inch. Okay?
Does it do connection types too?
some.
But that has a different module, connection module. I don't have that. But RAM has that. Okay? And if you see the garter beams, 21 by 50. That's the garter size. Okay? So that's your beam. That's your design. Okay? Beam design, not the column design. Okay? That's the beam design. And if you want to see what is going on at the roof level, you can see that. Again, the roof level doesn't have any change in loading, so it should be same. What about the floor levels? First floor level? Again, we did not change any loading, so the beam size will be same.
Okay. Okay, I'm going to.
So beam design took only what? Less than 1 minute, 10 seconds actually. Let's go into the column designs first. Now, again, there is a difference between this one and concrete. You were in my concrete design. In concrete, we cannot do that because what? The same column takes moment also. Okay? Same beam takes moment because the concrete connections are rigid connections. Okay? Even though we are saying those are gravity columns, but that column takes moment. Okay? Here, for a steel structure, it's much easier because you are saying that the gravity beams don't take any lateral loading. In concrete, you cannot just say that because those columns will be taking lateral loadings. Okay, for columns, again, I'm going to use the same code. And as I said, I'm a fan of, not fan, I use LRFD always. I don't use ASC. Design defaults, that's okay. Trial groups, okay. Trial groups means that I want to use the optimum number between W14, W12 and W10. Which one gives me the optimum design? Okay. Optimum design means I'm going to say that okay, I want a W14 by 68, whereas a W12 by 50 is sufficient. If that is the case, then the program will choose a W12 by 50, okay, because that's the more cheaper. So I can use W sections, or I can use HSS rectangle, or I can use HSS round. It will give me all the options. Okay. I'm going to say okay. Assigns bracing, it's already done that. Now I'm going to process design out. Done. Okay?
Yeah. You will learn that when we are
In chapter 5 and 6. What does that mean? It's called interaction state or interaction diagram. Okay? The value of interaction. Now if you see, there is no red because it designed that. There is no red. It's all blue or green. So if we see one of them, it's called view update. Okay, click one of the beam columns. I will see that. Oh, I forgot to show you the beam update in the beam. So when we get out of that, I'll show you. So if I see this column, okay. Now I'm not seeing this one because these are, even though these are lateral columns, right? It's a moment frame. This is a brace plate. These are lateral columns. Right now they are only designed to take gravity load. Gravity was their design. So they're not designed for lateral. So I'm going to use a normal gravity column. And if you see the optimum numbers, the design is W10 by 49 for the first third floor, and the second top 3 floors is W10 by 32. Remember, I added splicing at the third floor. That means I'm saying that change the section after the third floor. What is the advantage? From 49 to 33. So I'm getting some economy. If I want to use a W14 by size, this would be the size. Okay. Again, it's 14 by 53, whereas 10 by 49 was. If I'm using a W12 by, then 12 by 53, again, options. So these are my options. Okay. And the values of interaction is given as 0.69, and 0.69 means 0.69 should be somewhere here. This color, right? Right? No, actually it's points. How much was that? Oh, now I'm talking about this one. It's 0.83. Right? First floor is 0.83, and 0.83 is between this one. This one. Okay? Okay, my columns are done.
I want to go back to
Beams once more. Typical. And I want to show you, say, for this one. Okay? W12 by 19, composite beam, how many stars, all this. And you can see view results. That means it will say how much moment it is taking and what are the load combinations it is doing, everything. What is the deflection, how much. Another thing you can see view diagrams. That means what is the moment diagram, what is the shear force diagram.
Oh, can you go to the beam moment frame and look at the shear diagram?
We're not done with moment frame. Okay, you can do that. Or if you want to see the loading, that's your loading diagram.
okay. Okay, so we are done with that.
Now I want to do the frames quickly. I may need another 5-10 minutes more. Okay. No, you cannot ask me questions. No. Okay. So basically, what we need to do is give seismic loading and wind force. Okay. So let's go with the seismic loading. Now you have to do very carefully the video or picture because you don't know anything on that. Sorry for that. Seismic. Okay. And I'm going to use an equivalent lateral force method. Unfortunately, or fortunately, usually we should not be using for a 6-story building. Equivalent lateral force method is not applicable anymore because you have to use a dynamic analysis. We are doing a static analysis. Okay, and I'm going to use a and. So I'm going to change a bunch of numbers. X direction we have brace frames, eccentric brace frames. That's actually 7. Sorry, concentric brace frames special is 7. In the Y direction it's special moment frames. That's 8. These are called response modification factor, R factor. You will learn it in your senior design. Importance factor for this building, office buildings are usually 1.25, that means it's multiplied by 25% more. Soil site class D, if you do not have that. SS value is actually given in your
Hold on a second.
handout. SS value is given here. Okay, these are the two values we are going to take: 2.186 and 0.696. What is that? So it's 2.186
Point.
696.
This category is a 3.
And orthogonal conditions. Orthogonal conditions is when we have multiple frames coming in one single column. Okay, two frames. We don't have that, so we do not need anything else. Other than that, these are self-calculated. And we are going to do a little bit wind also. Okay, only thing we need to do is say 7, 8, and the rest same remains same. Okay, now we are going to analyze it. Select all. Unstable structure. What is that? That means up. What happened? Okay. Which means, remember my columns for the frames are designed for gravity load and W10 by 49 or those. For seismic load, these are going to fail, and failing in some way that they cannot stand. They are way too much. Remember this thing. I will be saying this thing in our class when we are going in a frame design. Okay, these are called P delta effects. Okay, that means the deflection is so much that additional moment is generated and it fails. So what we are going to do, we are going to I'm going to erase all, not erase, not showing the gravity system. What we are going to do is we are going to change the column sizes to a huge size, which is W14 by 398. Okay, and I'm going to change the beam sizes also by W18 by 211.
It's only for the
Lateral system, not for that. Now I'm going to go analyze it.
Done.
You follow me what I'm saying? That means my column sizes were and beam sizes were so small that it failed.
Can you do it for the, oh no, this one is something else.
Huh?
Does it have an option where you figure it out what's most optimal?
No, that you have to do it by yourself. That's why we are the engineers. We have that. Now I want to show you a dance. I want to show you that one. Okay. So I am going to use one of the X forces. Okay, not 200, maybe 20, and animate. That's how the building will behave under seismic load in this direction. Okay, the building movement.
Okay.
Can you show it from the other view?
Yes, I'm going to.
Other view means other direction.
I mean like, looking at an elevation.
Hold on a second. And what about in the Y direction? What is wrong with that? Same scaling, what is wrong with that? The reason is, other direction is moment frame. Moment frame is very flexible compared to base frame.
That's normal, I've seen a building do that.
No, it's not. Honestly, it's too much because I'm scaling it to 20 times. This is how the building will behave in real. Still a lot. Still a lot.
It's like going like 20 feet, if that's right.
No, yeah, your moment frames are not enough. Okay, so if I'm going to do that, You want to see from the other side, right? That's how the building will behave.
That's still stable, right?
No, your moment frame needs to be bigger. It's not sufficient, I would say. Okay, so that's your design, not design yet. Now I want to go quickly, couple of things, analyze. I need to do some load combinations, which is, because remember, 1.2 dead load, 1.6 live load plus seismic load.
Mhm.
One 1.54. Take this number also. I'm not sure whether you are familiar with the numbers called redundancy. Have you heard the name redundancy? Usually, if you are in the senior design class, most of your teachers will say that use 1.3, okay, which I don't buy it. Okay, if you 1.3 means you pump up your loading by 30%. Okay, I need to do quick things, couple of things, which is called some additional checks for California, which is called standard provisions. Alright, yeah. Process member code check. Look at the columns. I pumped up to what, 14 by 390? Still doesn't work. Okay? Because we have fewer. Why it doesn't work? Let's check it one. Interaction is 3.31. Way too much load. Okay? That means if I were the designer, I would put another frame in the middle. Right now the whole thing stands on that. I'm not going to do anything on that. You know how to do that. You can go and check. Say for example, you can do something like still doesn't work. So basically I have to add another one. Another provision is called seismic provision, that you have to do it later. Okay. And that comes from, there is an omega factor, or which is called overstrength factor. That's, again, these are all part of the code. Okay. Now also you have to assign frame type. The first one is concentrate special moment frame. And the next one is process, member code check. All of your braces are failing. This is, I'm not worried because my deck is on the other direction. This part is not a problem. Okay, but okay, if you go view update, what is wrong with that? No checks. Okay. So one more.
Can you
Okay.
convert it to
Huh?
Revit? Can you convert it to Revit
Yes,
too?
right.
Okay.
One more quick, yeah? So if you look into that, these are all going to give me blue, green. But does that mean that they are designed properly? No. It means that we have done that, but not properly. It's not right. So when you come, a lot of students come to me and say, oh, these are all green. No, these are not green, doesn't mean that you are done. I'm going to use a 36-inch by 36-inch plate. Quickly, geometry.
What is this?
Foundation.
Generate for concrete. Just give me 3-4 minutes. Okay, my foundations, the spread footings are done. If you look into that, one of them, it will be 12 feet by 12 feet. Bar size 7, number 7 bar, 13 number 7 bars each direction. So your foundation is done. Okay. What about this one? These are not done yet, so we can click on that. And what does it say? All springs are in tension. So what we need is pump up the size. Okay, so
It works. What is the size of that
foundation? Now you'll see that the size of the foundation is 77 feet long, 24 feet wide, 6 feet thick.
But is that normal?
Yeah. Okay, and reinforcements. Okay. Number 8 bars, all the designs are done. Okay? So if you are taking steel, the concrete, you know all the reinforcements. Okay? And you can do the rest. That's it. I'm done. Can you turn on the lights, please?